Alright guys, so we are now into section 2.4 of the book, so this is still in the first unit of study though, and we're studying how to solve for constantly accelerated problems. So constant acceleration problems. In the last video we looked at graphing and representing velocity versus time graphs, and the slope of the line was the acceleration. So this is a new concept, and I'm just going to go through it again, even though we spoke about it in the last video. So acceleration is a ratio of the rate of change of velocity. So it's the rate of change of velocity, so it's how much your velocity changes, so delta v, divided by how much time goes by. So that's what makes it a rate. And it's also that slope of that graph. So we've only studied horizontal motion, so we're only dealing with the x direction, but eventually we will deal with y direction when we start moving up and down. So ax and vx here, it doesn't really matter. You can just say a equals change in v over t. So the definition of acceleration is the rate of change of velocity, or how quickly velocity changes. Our unit that we're going to use for acceleration is meters per second squared. This slide goes through and calculates the acceleration of a car based on how fast it gets to in a certain amount of time. So that's what that is. But meters per second is what I think is the good indication of what's going on. So it's tracking how many meters per second the object's velocity is changing each second that goes by. So you're going to keep adding this acceleration value to the velocity for each second of change that goes on. And we did this with the graphs. So the Corvette versus the Sonic. The Corvette has a greater slope, which means it has a greater acceleration. So it reaches the speed more rapidly. Okay. Again, there are links here that if you want to look at the videos to help you in your Google Slides, you can. All right. So again, if you have a positive slope for acceleration, that means a positive acceleration. Again, just means going to the right. If you have a horizontal line where the acceleration is 0, that means it is not changing its velocity. So that's like a constant velocity here. So it's just whatever this number is, it's staying at that velocity in that direction. And then a negative acceleration would mean moving to, or the acceleration is directed to the left. So not necessarily moving to the left, but the acceleration is directed to the left. So that's a negative slope on the line. So let's kind of talk about how acceleration impacts velocity, or how it changes the velocity. And one of the key points I'm trying to make here is to overcome a really common misconception, which says that if you have a positive acceleration, you speed up, and if you have a negative acceleration, you slow down. That is not always true. So you can't use that as your rule. It is not accurate. What you need to do is you need to look at the directions of the velocity and the acceleration and decide what is happening to the object and how the acceleration affects the velocity. So I'm going to go through some examples here, and hopefully that clarifies it in these examples. So it says if the acceleration of an object agrees, and I use the word agree, or points in the same direction as the velocity vector, then the velocity would increase. So if you look at this picture, if we're measuring this blue car here, this blue car has a velocity, and I'm going to call that a positive velocity because it looks like it's going to the right. If we have an acceleration that is also positive, then they agree, they're both positive, so the car speeds up, so it's going to go, and the velocity vectors would get larger. So that is a really common case. The way that I think about this often is kind of like if your acceleration is in the same direction as your net force. So if you imagine a force like you just push or pull on something. So if we had this car and it was moving to the right, and we started pushing on it more to the right, it would speed up or go faster, so the velocity would increase. So that's how I would look at it. Now I'm going to give you a counter. I'm going to give you a counter example by basically just flipping this situation over. So, and I just actually flipped the image over in this picture. So that's why the writing's backwards. So if we look at this car, it's moving to the left. So it has a negative velocity. And if we want it to accelerate it to the left, the direction of acceleration would go to the left. and we would talk about what's happening to this car. So again, if you think about the acceleration as sort of the pushing part or the agreement, so these are both negatives. So since they're both negative, it would increase, the velocity would increase. So this car would go from a smaller velocity to a larger velocity just in the negative direction. So this arrow is getting bigger as we move to the left. Again, if you think about the pushing aspect, if the car is moving to the left and we want it to go faster, we would push it to the left. So the acceleration would be, they'd both be in the negative direction. So that is increasing velocity, or I think commonly people say speeding up. If we wanted something to decrease velocity or slow down, you want the opposite kind of relationship. So if the acceleration of an object and the velocity of an object are disagreeing, so disagree points in the opposite direction, so you can see these arrows are pointing in opposite directions, then you're going to get the case of the velocity decreasing. So for this first one, if I ask you what kind of velocity is this, you would say it's a positive velocity. So this is directed to the right. And if we look at the acceleration vector, it's going the opposite way. So those disagree. So they point opposite directions, and it makes sense that they would slow down. So again, if you're applying the force in the direction of the acceleration, if it's moving to the right, you would push on it going the opposite way, and that object would slow down. So it's starting out with some velocity, and that velocity is going to get smaller, and the arrow is going to get smaller as time goes by. If we flip that over, it is the exact same scenario. It's just going the opposite way. So we have a negative velocity. Direction of the acceleration is directed to the positive or right. So they disagree, they're going opposite directions, so you're going to slow down. So the car is moving to the left with some speed, or velocity, and we're going to push on it going the opposite way. So if you push against it, it's going to make the arrow get smaller, and that would be velocity decreasing or slowing up, slowing down, same thing. So that is really the way that you have to keep track of it. It is not related to whether it's just positive or negative. Again, positive or negative are only directions. So it's a direction. It tells you the direction. You have to look at how they agree or disagree, those two vectors, the velocity vector and the acceleration vector, to decide if it is increasing velocity or decreasing velocity. That is a really, really, really important point. It is a really common misconception, and you will have to do that on your assessment. So we're going to continue with this concept and kind of look at the motion map. So again, the dots represent the particle moving and each second of time that goes by. And we have our velocity vectors in green here, and we have our acceleration vectors in orange. And from this diagram, we're going to answer some questions, and we're going to have a couple questions about this one diagram. So it says, the motion diagram shows a particle that is slowing down, the sign of the position x and the sign of the velocity vx r. So let me give you a second to try to figure this one out. So I would say that the position vector is negative because it moves from here to here, so I would call that displacement as negative. And the velocity is also negative because the velocity is going to the left. So I would say that's B, which is the correct answer, which is negative and negative. Looking at the next question, the motion diagram shows a particle that is slowing down. That's important. And we want to know what the sign of the acceleration is. So we want to know what is the sign of that acceleration. So it's either positive or negative. You have to decide. Slowing down, you got to remember what kind of relationship. Does it agree or disagree? If you look at our vector here for velocity, it is going to the left, so I'm going to call that negative. And our acceleration vector points in which direction? It's the positive direction. So since it points in the positive direction, they disagree, and it slows down, so this answer is going to be A. Okay. A couple more of these types of questions. We want to look at the 4 motion maps here, and we want to decide which motion maps correspond to a positive acceleration. So I'm going to let you answer that question now based on their motion. So you got to look at, is it the velocity getting bigger or smaller? And does that mean there's agreement or disagreement? Remember, you want to look at the velocity vector and the direction, whether it's positive or negative, and the acceleration vector, and whether it's positive or negative. So looking at this first one, that's a positive velocity. Looking at B, that's also a positive velocity. C and D are both negative velocities, so they are going to the left. So we've established that. And now we got to look at whether they speed up or slow down. So in A is speeding up, so that means that the acceleration vector has to agree. So that's they agree. In B it is slowing down, so that would be disagree, so that's a negative acceleration. C, it is speeding up and we want agreement, so if our velocity is negative, our acceleration should also be negative. And then finally for D, we have a negative velocity, it's slowing down, so we want a positive acceleration. So overall, the motion diagram is corresponding to a positive acceleration would be A and C, and then the ones with a negative acceleration are B and D. Okay, so we're getting into the next part of the lesson, which is dealing with how to solve problems that have kinematics descriptions and not just using graphs. So one of the first things that we need to do is just clarify all of the different variables that we measure in these ideas. So in these problems, they'll give you information about acceleration, initial velocity, I'm going to say final velocity, VF, and then position, initial, final position. We can measure displacement by subtracting these two, so we already know this calculation is the final minus the initial. And then change in time. So I have given you kind of a overall view of all the different ideas that you could measure. Sometimes the final is just left out, so it just means later in time. So initial velocity and then a velocity later, that's fine. Some notations use finals and some don't. So I also gave you the units. So the units are really important because they are helpful in describing the different types of measurement. So when you see a unit, it tells you information about, okay, is this a position, is it a time, is it a velocity, is it an acceleration. Remember, directions are just positive or negative. I missed out a negative sign there. So if you see a plus or minus, that's a direction associated with it. That's all it means. So once you have those variables kind of in your head, you can start working with them. And these are the four equations that we're going to use. Oops. Excuse me, fix that. These are the four equations we're going to use to describe and calculate the different types of problems and solve them. You don't need to write out 1, 2, 3, or 4. I think it'll just be easier to refer back to them in this manner, so that's why I'm doing that. So the equations just relate 4 of the 5 variables. And then there's one variable that's not missing, or it's not in the problem, it's not given, it's not involved, so that's the 5th variable. So there are always 4 variables in each of these 4 equations. So the steps in solving the problems are pretty basic. One other thing, these equations only work if the acceleration is constant. That is key. So we can study a constantly accelerated motion. If we didn't have a constantly accelerated motion, which is definitely possible in real life, then you would have to use calculus. So that our physics class is not including that. So steps in solving kinematics problems, first thing you're going to do is draw a picture. So either a motion map or just a little sketch of what's going on. It's basically a dot or the object and a couple arrows, like just showing how the motion is proceeding. Then you're going to list your givens in a table. I'm going to demonstrate all these steps in a couple of example problems and then have you guys work on some. And then you're going to determine which equation to use. Steps 2 and 3, those are the ones that usually give people trouble in the beginning. Once you get them down, it becomes very formulaic and you're just going to do some algebra at the end and make sure that you think that your answer seems reasonable and remember your units and things such as that. So let's go ahead and start with a problem and we'll demonstrate this procedure. So the first example here says a car moving at 20 meters per second hits the brakes and undergoes an acceleration of -4 meters per second for 2.5 seconds. Okay, so we have a car. So I'm going to draw a quick sketch of a car. And again, I'm trying to use a mouse here, so it's not the best car picture, but that's a good enough car. And it says the car is moving to start, so I'm going to have an arrow going to the right. The reason why I have it going to the right, this is a positive value. It didn't say negative there, so I'm going to assume that's positive. So it's moving to the right, and then they hit the brakes. So if you're in your car and you hit the brakes, what should happen to your velocity vector, your arrow? When you hit the brakes, you should slow down as long as your brakes are working. So I'm going to make this arrow get smaller. Okay, so that is the sketch. That's good enough for a picture. It doesn't have to be fancy. The next part we're going to do is set up our table. So I just make a table like this. You can organize your data vertically or horizontally. I think this kind of setup is useful in arranging your information. So I'm going to write the 5 variables that are in these problems in the top of the chart, so or table. So I have delta x displacement, vi initial velocity, vf final velocity, a for acceleration, and delta t for change in time or time period. And then what you have to do is you just got to pull your information out of your problem. So you're trying to read and use context clues and units to decide what are these things. So cars moving at 20 meters per second. Meters per second, if we go back to our list of things, meters per second is a velocity, so it's one of these two, and it's either the initial or final. And I'm going to say it's moving at 20 in the beginning, so I'm going to put that as the initial. So I'm going to put 20 meters per second. Again, just get in the habit of writing positives or negatives. It is positive, let's go into the right. You hit the brakes and undergoes an acceleration of -4 meters per second. It tells you an acceleration of, so that's pretty directly stating that -4 is the acceleration. I always write the units in the table to make sure they match up and make sense at all. Finally, 2.5 seconds. Seconds measures time, so that's going to be in that box. Okay, so we have information for 3 out of the 5. If you have 3 out of the 5 variables, you're good to start solving and trying to select an equation, because you only need 3 out of the 5, because the equation has 4 variables in it. If you know 3 out of the 4, you can solve for the 1 variable that's missing. So in this question, it says, what is the car's velocity, final velocity? So I'm looking for VF. So if you look at this, I have a question mark for what's given, or what I'm looking for, and then I have the numbers in for what's given. There is one box that is not filled in. So if I go back to that box is the one that I'm going to use to decide which equation to use. So if I come back to these equations, I can look through all these equations and try to figure out, okay, which of these equations has all 4 variables that I want in my chart. Or I can go to the variable that's missing or not given and say that is the one that is not in that, so the equation has to have all the rest. So that is the way we're going to look at this. We're going to look at what's not given and then decide that's the right equation. So delta x is not given, so that's the one we want. And I'm going to try to make a picture here. Move this up a little bit, sorry. I'm going to take a picture of the equation because it is easier than typing it or writing it out. So I'm going to send that here and move it down. And then we're going to work through the problem. So it's not too complicated. It's just kind of doing the math and figuring stuff out. So I'm just going to write out the variables in the spot. So VF is what I'm looking for. VI was 20. The acceleration is -4. And then I'm going to multiply that by 2.5. So if I keep solving, VF is, again, what I'm solving for, so I don't have to do much algebra here. I just have to plug in on the right side and solve. So it'd be 20, and then -4 times 2.5 is a -10. Which is going to give me a +10 meters per second for my final answer or solution to this problem. So kind of looking at this and making sure it makes sense. +10, it seems to make sense. Yeah, it's the car's supposed to be braking, and braking would make it slow down, or the velocity to decrease is a better way to describe it more accurately. So the object value got smaller. So as time went by, we did that. So we could check this if you wanted to kind of think about it with the chart. So we did this before, so velocity in meters per second. And we're going to track the velocity as time goes by, so the time in seconds. And we need to track it for about 3 seconds of time. So if I start out, I'm going 20 meters per second. And then that's at time equal to 0. That's the initial time. At 1 second, we're going to subtract 4. So if I subtract 4 here, I'd be at 16, because the acceleration, the change in velocity per change in second. So this is 1 second of change, and this is -4 meters per second of what we're adding to the velocity. So at 1 second, I'm going 16. At 2 seconds, I'd be going 12. At 3 seconds, I'm going to be going 8. And our answer is for 2.5. So 2.5 is in between the 2 and the 3, and it's halfway between 2 and 3, and halfway between 12 and 8 is 10. So yeah, this seems to make sense. It seems to check out. We could plot a graph. We could do all sorts of things to verify this, but these equations work. Like the way that they work, they work together. So you could use a different equation, one of the other four, and solve and still get the same answer. Okay, we're going to keep moving. In this one here, the next one, it says, how far did the car travel? That up. There we go. Shoot. How far did the car travel? So we're going to kind of do the same thing. So we're going to use this picture again. So I'm just going to do another. I'm going to grab all the stuff that I had my information here. And I'm going to send it to this page. And I'm going to try to move it up. There we go. So nothing changed there. Now we're just looking for, So we're looking for how far the car traveled. So we're no longer doing this aspect of it. So how far it traveled is basically part B, and we're solving for delta x. So we need an equation with delta x. Luckily, we have equations with delta x in it. The only equation we can't use is number 1 because it doesn't have a delta x. So we can use any of these equations, 2, 3, or 4. And I would say pick the one that looks easiest. So whatever one you feel is easiest, I would select. I would pick number 4 because this one has a squared and it's not solved for delta x. 2 is fine, but it's got another squared and it looks like more calculations. This looks a little simpler, so I'm going to use that one. So I'll take a picture of that equation and use it here. So if we use that equation and we just type it, because again, that'd be easier. Delta is not the easiest thing to get to, but let me try to pull it out. Okay, so delta x is equal to 1/2 VI. VI was 20. VF we said was 10. And time is 2.5. So we're going to put that in the calculator and solve. So 20 and 10 is 30, half of that is 15, and 15 times 2.5 is going to give me 37.5. So our answer here is a positive 37.5 meters, positive because it's moving to the right, which makes sense. And again, you could track this and try to figure out if that is a good amount of distance, and it seems reasonable. Okay, so we're going to practice 2 more of these and get through them. So in this one, the car starts from rest and accelerates at 3.5 meters per second. How far has the car moved when it is traveling at 25 meters? So with this one, again, we're going to start out with the same steps. We're going to draw a picture. I'm not going to be as artistic in this one. So we have our dot, and it's going to move to the right and speed up. Starting at rest, so I'm going to write rest down. Rest is an important word. I would say include that in your pictures. If you're at rest, that means that your velocity is equal to 0 because you're stopped. So we have that set up. Let me set up the chart and plug in. So we got delta x, vi, vf, a, and time. So starting at rest, that's the initial, it's going to be 0. Accelerates at 3.5. So it tells you the acceleration in meters per second squared, also implies that it's an acceleration. And we want to know how far the car has moved when it's traveling at 25 meters per second. So 25 is the final velocity, or the velocity at the end of the accelerating time period that we're trying to figure out. And we're looking for how far. So how far is displacement? So the thing that I don't care about is time. So that is the thing that is missing. So I look for the equation without time in it. So going back to the equations list, the one without time is this one. Again, I'm going to take a screenshot or just a quick clip to get that and start working with it. Okay, so let's go ahead and try to take this out. So VF is 25, and we're going to square it, and that's equal to the initial velocity, which is 0, so 0 squared, plus 2 times 3.5, and then I need the delta again, so let me get that here. Yep. And then it's delta x. So doing this math, 25 squared is 625, 0 squared is 0, 0 plus anything is still just that number, and this is going to be 7, and then I'm going to have delta x there. Didn't copy. Okay. So we're going to take 625 and divide it by 7, and that would be equal to delta x. And that solution is 89.3 meters. It is not exactly 89.3 meters. It's close to that. I just rounded to 0.3. You don't need to go past 1 or 2 decimal places. That's fine. We could also have a follow-up question like how much time went by, but this question didn't ask it, so I'm going to keep going. Again, once you have 4 out of the 5, you can use any equation as long as it has t. All right. Last one here, I've already worked out a little bit, so let me see if I can incorporate that. So it says a car traveling at 7 meters per second accelerates at 0.8 meters per second squared for a distance of 245 meters. We want to know what's the velocity at the end of the acceleration, and then how long does it take for this to travel the 245 meters. So again, first step is going to be, sorry, to get to selecting. There we go. So the first step is to draw the picture. So I have a picture that I got a picture of a car off the internet. It says car is traveling at 7 meters per second, so it's moving, and then it accelerates. So if the acceleration and the velocity vectors agree, it's going to speed up, so that seems right. Then we go to the chart. So if we fill in our chart, I've already done this for you. 7 meters per second, that's the initial velocity. 0.8 meters per second squared, that's the acceleration. The distance traveled, or the displacement, is going to be 245 meters in that time period. We're looking for the velocity final, so we're looking for VF. So in part A, I need an equation with these three, or the one without time. So that was the same equation we just used, the squared one. And I just plugged in and did the math. So again, it's just as simple as taking those values from the chart, putting them where the letters are, and then doing algebra at the end. So at the end of this time period, or at the end of this acceleration period, where the 245 meters, this car is traveling at 21 meters per second. For part B, it asks how long does it take, so we're looking for the time. We're solving for that. So we need an equation with time in it. We can use any of them. There are two that are about equally in difficulty, so I use this one first. So 245 was the displacement, 1/2. Initial velocity was 7. Final velocity we got over here is 21. And we're looking for time. You're going to solve. So it's 28 divided by 2 is 14. And you're going to solve for t and get 17.5. If you didn't like that one, you didn't want to use that one because I don't know why, you just didn't. You could also use this equation. So VF is 21, VI is 7, A is 0.8. We're looking for time. You subtract, get 14, divide by 0.8, and you will get the same answer, so 17.5 seconds. Again, any of the equations, as long as they have time in them, you could use to solve. So there's one other equation. I didn't use it because I had 2 times, and that would make it a little bit more complicated. You'd have to use like quadratic formula or something, and I try to avoid hard math whenever possible. So hopefully this is a good resource for you guys. Come back and look at these problems if you need help solving or you need a model of, again, what we're doing for the steps. Take care. Be well.